Hello everyone. In this lecture series, I'll be covering the Unit 4 of Subject Fundamentals of Mechanical Engineering. The Unit 4 is Introduction to Fluid Mechanics and Applications. In the lecture 0 of this series, I have covered the syllabus of this unit. In lecture 1, we will be starting the Introduction to Fluid Mechanics, the part 1 of this unit. First is, what is fluid mechanics? So first we will discuss what is mechanics. Mechanics is the oldest physical science that deals with both stationary and moving bodies under the influence of forces. The branch of mechanics that deals with the bodies at rest is called statics, and the branch which deals with the bodies in motion is called dynamics. Then, what is fluid mechanics? Fluid mechanics is defined as the science that we deals with the behavior of fluids at rest, that is fluid statics. When the fluid is at rest, that is fluid statics, and the study of the motion when the fluid is in motion, the study of the behavior of fluid when it is in motion, that is fluid dynamics, and the interaction of fluids with solids or any other fluid at the boundaries. The behavior of these type of fluids in rest or in motion, or when they are in interaction with solid or any other fluid, the study of behavior of these fluids is termed as fluid mechanics. Fluid mechanics is also referred to as fluid dynamics by considering fluids at rest as a special case of motion in which the velocity is zero, with zero velocity. That is the special cases of motion with zero velocity. A substance exists in three primary phases. These three primary phases are solid, liquid, and gases. When the substance is in liquid or gas phase, it is referred as a fluid. The distinction between a solid and a fluid is made based on the substance's ability to resist an applied shear or tangential stress, the applied shear stress or tangential stress that tends to change its shape. A solid can resist an applied shear stress by deforming, whereas a fluid deforms continuously under the influence of shear stress, no matter how small that deformation will be, how small that shear stress applied on the fluid. Fluid is a substances with zero shear modulus, or in simpler words, we can say these substances cannot resist the shear force applied to them. Now, the next topic is fluid properties. What is a property? Any characteristic of a system is called a property. There are various properties of fluids, but then properties in general can be considered to be either intensive or extensive. There are two types basically, intensive properties and extensive properties. Intensive properties are those properties which are independent of the mass of the system, such as pressure, density. There are no dependency on the mass of that system. But the extensive properties are those which depends on the size or extent of the system, or which depends on the mass of the system, such as volume, mass, etc. These are extensive properties. So we will be discussing few properties of fluids. So the first one is pressure. What is pressure? It is defined as a normal force exerted by a fluid per unit area. We speak of pressure only when we deal with a gas or liquid only. The counterpart of pressure in solid is normal stress. In the case of solids, we discuss about the normal stress. But in the case of gas or liquid, we discuss about the pressure. Since pressure is defined as force per unit area, so the unit of this is newtons per square meter. And it is also called as Pascal. Newton per square per meter square. That is Pascal. So in this slide, we are discussing the units of pressure. The pressure unit, Pascal, is very small. So in general, we use kilopascal. 1 kilopascal is equal to 10 raised to the power 3 Pascal. And we also use megapascal. 1 MPa is equal to 10 to the power 6 Pascal. These are commonly used as the Pascal unit is very small when we talk about in general practice. So there are some other units are also exist. These are the conversion given here. 1 bar is equal to 10 raised to the power 5 Pascal, zero point 0.1 megapascal, that is equal to 100 kilopascal. Then 1 ATM is equal to 101.325 Pascal, that is equal to 101.325 kilopascal. Then the conversion in bar. Then another unit is 1 kgf per centimeter square. That is equivalent to 9.807 Newton per centimeter square. And when we talk about in Newton per meter square, the conversion is given as 9.807 into 10 raised to the power 4 Newton per meter square. That is also equal to Pascal, as 1 Newton per meter square is equal to 1 Pascal. When we convert it into bar or in atmospheric pressure, uh, 1 kgf per centimeter square is equal to 0.9807 bar. That is equal to 0.9679 atm. These conversions are given here in bar and in atmospheric pressure. So this is about pressure. The actual pressure at a given position is called as absolute pressure, and it is measured relative to the absolute vacuum, that is absolute zero pressure. The actual pressure is measured relative to the absolute vacuum pressure, which is absolute zero pressure. Most pressure measuring devices, however, are calibrated to zero in the atmosphere, and so they indicate the difference between the absolute pressure and the local atmospheric pressure. This difference is called as the gauge pressure. So what is gauge pressure? Here, P gauge is equal to P absolute minus P atmospheric pressure. This is, here we can say P gauge is equal to P absolute minus P atmospheric. This is absolute vacuum here, this line where P absolute is 0. The P absolute, this, and P atmospheric, P atmosphere. So P gauge can be calculated as P absolute minus P atmosphere. P gauge can be positive or negative, but pressures below atmospheric pressure are sometimes termed as vacuum pressure. Then what is vacuum pressure? The P vacuum is equal to P atmosphere minus P absolute. The next property is density. It is defined as mass per unit volume. Density is denoted by rho. Rho is equal to mass per unit volume, m divided by v. The unit of m is kilogram kg, and the unit of volume is meter cube. The unit of density is kilogram per meter cube. The reciprocal of the density is termed as specific volume. That is volume per unit mass. So V is volume per unit mass. Here, 1 by rho, the reciprocal of density. The third property is specific gravity. Sometimes the density of a substance is given relative to the density of a well-known substance. Then it is called as specific gravity or relative density, and it is defined as the ratio of the density of a substance to the density of some standard substance at a specified temperature. Usually that standard substance is taken as water at 4 degrees centigrade. Here the standard rho of water is given 1000 kg per meter cube. So specific gravity is rho, for which we have to calculate the specific gravity divided by the density of standard fluid, which is generally taken as water. The next property is viscosity. What is viscosity? When two solid bodies in contact move relative to each other, a friction force develops at the contact surface, and the direction of that force is opposite to the motion. So viscosity is defined as the property of fluid that refers resistance to the movement, of one layer of fluid over another adjacent layer of the fluid. We move with relative ease in air, but not in water, and moving in oil would be even more difficult. This is the resistance offered, this is because of the resistance offered by the fluid. So it appears that there is a property that represents the internal resistance of a fluid to motion. And this particular property is termed as viscosity. And when we are discussing about viscosity, there is a law, which is Newton's law of viscosity. It states that the shear stress on a fluid element layer is directly proportional to the rate of shear strain. And this rate of shear strain is equal to the velocity gradient. So suppose there are two layers, two fluid layers at a distance y and at a distance y and y plus dy. This gap is dy. And there are two velocities, two different velocities. The layer 1, the velocity of layer 1 is u, and the velocity of layer 2 is u plus du. So the top layer causes a shear stress on the lower layer, while lower layer causes shear stress on the top layer. Here, so this shear stress tau is directly proportional to the velocity gradient. Yeah, rate of shear strain, that is du over dy. So when we remove this proportionality, there is a constant comes, which is mu. Here, constant of proportionality is mu, which is known as coefficient of dynamic viscosity. This mu is coefficient of dynamic viscosity, and du over dy is known as the velocity gradient. The next property of the fluid is weight density or specific weight. Weight density or specific weight of a fluid is defined as the ratio of weight density of a fluid to the volume of the fluid. In other words, it can also be defined as the weight per unit volume of the fluid. It is represented by W, mathematically weight of the fluid by volume of the fluid. So what is weight of the fluid? Weight is M into G divided by volume of the fluid. Then what is M over V? That is rho into G. So W is equal to rho into G. Next is the types of fluid, which are of two types. One is Newtonian fluid and the another one is non-Newtonian fluid. How we can categorize these two types of fluid? We can categorize on the basis of Newton's law of viscosity, which we have started just now. So what are Newtonian fluids? Fluids that obeys Newton's law of viscosity is called Newtonian fluids. A real fluid in which the shear stress is directly proportional to the rate of shear strain, or we can say the shear stress is directly proportional to the velocity gradient. These are termed as Newtonian fluid. So examples are water, mineral oil, gasoline, and alcohol, etc. These are termed as Newtonian fluid. Here is a graph is also given, the Newtonian fluid, which follows the Newton's law of viscosity. And the next is non-Newtonian fluid. What are non-Newtonian fluids? These fluids are which do not follow Newton's law of viscosity. The fluids which are not following the Newton's law of viscosities are termed as non-Newtonian fluids. A real fluid in which the shear stress is not proportional to the rate of shear strain, or it is not proportional to the velocity gradient. These are termed as non-Newtonian fluid. The behavior of these fluids can be described in these ways, further these ways. So in graph, we can also see like dilatant fluid, pseudoplastic fluids, Bingham plastic. These are not following the Newton's law of viscosity. So we will be discussing these. First is dilatant. What is dilatant type of fluid? Viscosity of the fluid increases when shear is applied, also known as shear thickening. Like example, quicksand, corn flour, and water silica. The other one is pseudoplastic type of fluid. Pseudoplastic is the opposite of dilatant, in which the more we apply the shear stress, the less viscous it becomes. The viscosity decreases. It is also known as shear thinning fluids. Example is ketchup. The next one is rheopectic type of fluids. Rheopectic is very similar to dilatant. In this, when we apply shear, the viscosity increases. Here is a difference with dilatant is like in this case, viscosity increased is time dependent. This is time dependent property. Example, gypsum paste, cream, etc. The other one is thixotropic. What are thixotropic type of fluid? Fluid with thixotropic properties decreases viscosity when shear is applied. The more shear is applied, the viscosity is decreases in this type of fluids. This is also a time dependent property. Examples are like paint, cosmetics, glue, etc. The other one is Bingham plastics. What are these? Materials, Bingham plastics are the materials such as toothpaste can resist a finite shear stress and thus behave as a solid, but it deforms continuously when the shear stress exceeds the yield stress and behaves as a fluid. These are the types, these are the properties of non-Newtonian fluid. So we have discussed about the properties of fluids, and in further videos, we will covering the other part of the unit, other topics of the unit. These are some references. Some books are given here. The syllabus link is also given here. Thank you.